In Chapter 10, we're going to discuss radicals, which include square roots, cubed roots, fourth roots, nth roots, and so on. The key terminology for Lesson 10.1. Number 1, the number c is a square root of a if c squared equals a. The principal square root of a non-negative number is its non-negative square root. The square root of any whole number that is not a perfect square is an irrational number. The radicand is the expression under the radical sign. The number c is a cube root of a if c cubed equals a. And the number n in the expression nth root of a is called the index. And this will make more sense once we start looking at some examples. So here we have several examples, and for the first few examples it just says simplify. All numbers have two roots. Now, number 9 actually is a perfect square because both the numerator, 225, and the denominator, 169, both of those are perfect squares. Now, with the negative sign out in front, that's indicating that they want the negative root. If that negative sign wasn't there, then they would want the positive root. So just to revisit the idea that all numbers have two roots, if we had, for instance, the square root of 9, well, that could be 3, or it could be negative 3 if we wanted the negative root. And if they wanted the negative root, then they would have indicated that by putting a negative in front. So negative 3. The reason why all numbers have two roots, the principal root of square root of 9 is 3, is because 3 times 3 is 9, but negative 3 times negative 3 is also 9. So there's two roots for all numbers. So let's go back to our number 9 here. Since both the numerator and denominator are perfect squares, we can actually simplify this. The square root of 225 over the square root of 169, you could actually take the square root of them individually, and the numerator would be 15 and the denominator would be 13, since those are both perfect squares. For the square root of 256, they want the principal root. There is no negative in front, and that's how I know that, and that would be 16. It is also a perfect square. Decimals can also be perfect squares. We know that just the number 9 itself is a perfect square, so if you see 0.9 or 0.09 or 0.009, that is also going to be, those are going to be perfect squares. You should look into that. Perhaps they are perfect squares. So for number 11, that is actually going to be 0.3 or 3/10. So now let's look at some of these down here at the bottom. We have the square root of 562. Now, it does say use a calculator to approximate. So, because of that, 562 is not a perfect square. So, when you put that into your calculator, square root of 562, you get a very long decimal. All of your square roots end up being irrational numbers unless they are perfect squares. So, we're always going to have to approximate that. So for this problem, and we have to approximate to 3 decimal places, so we are approximately 23.707. And again, we're having to approximate these to 3 decimal places. So if they're not perfect squares, then you are going to have to do some approximating. There is a way to write them exactly and simplify them, and we will look at that in the next lesson. Now let's look at square roots and see what they look like when we are using function notation. Now we've evaluated functions before, but never with a radical sign in them or a square root sign. So if I want to find g of 5, that means I have to put a 5 in for my variable in my function. So when I simplify this, I'm going to get 10 minus 5 squared, which is 25. G of 5 is going to be the square root of negative 15. And therefore we would say g of 5 You can say does not exist or is not a real number, but does not exist as far as you know right now. We will talk about those types of numbers later on in the chapter. We get into imaginary numbers, but just remember that a square root is a number times itself. There is no number times itself that gets you another negative number, because a negative times a negative is a positive, and a positive times a positive is a positive. So there's no way that you can get a negative out of that. And once we learn about imaginary numbers, then we can deal with that a little bit better. So g of 5 does not exist, or it's not a real number. So if we wanted to find g of 3, then I would do the same thing. I would just replace my x with a 3, and g of 3 is going to be, looks like 10 minus 9. So g of 3 is going to be the square root of 10 minus 9, which is 1. So that means g of 3 equals 1. And we would do this for the other values as well. I'd plug in 0 and see what I get, plug in negative 2 and see what I get. So let's look down at number 20 where it says find the domain of the function. Now recall, domain are values that you can put in, your x values. So in the past we've looked at domain and said you should always assume all real numbers unless there's a fraction or a square root, like in this case. So there's certain numbers that we can't plug in. For instance, when we plugged in g of 5 into the previous problem, we said it doesn't exist. So the domain is, we can't say all real numbers, only certain numbers are going to work, because we're going to get imaginary numbers or numbers that do not exist. So when you're talking about a square root of x minus 4, its domain has to be greater than or equal to 0, meaning numbers that we put in have to give us numbers greater than or equal to 0, or positive numbers. We don't want any negative numbers. We can't deal with those right now. So when I have a square root like this, I'm just going to take my radical, and I have to have it greater than or equal to 0. When you solve, we would have to square both sides, which is going to get me x minus 4 greater than or equal to 0, because squaring a square root, opposite operations. And then I would add 4 to both sides, and that's going to give me x must be greater than or equal to 4. So the domain, if we write it in set builder notation, is any number such that x is greater than or equal to 4. It can be 4, because 4 minus 4 is 0, and the square root of 0 is 0, or any number greater than that. If we write it in interval notation, 4 would be the lowest number we could have, and it can be any positive number, so we would say to infinity. So these are the two different ways we could write the domain, either in set builder notation or interval notation. Now let's graph square roots and find out what their graphs look like. So just like we've graphed in the past, we're just going to need a couple ordered pairs to do that. So square root of x plus 5. Now we want to make sure that when we plug in numbers, we get numbers that we can actually take the square root of. So, you know, is there a way that we can get the number 4, because the square root of 4 is 2? So thinking ahead a little bit, if I plug in negative 1, that would give me negative 1 plus 5, which would give me square root of 4, which would give me 2. So when I plug in negative 1, I get 2. So I'm kind of thinking backwards. I'm working backwards a little bit. So let's see here. That got me 4. The next perfect square is 9. So what plus 5 equals 9? Well, 4 plus 5 would equal 9. And I can take the square root of that and get 3. So when I plugged in 4, I got 3. And let's think of another one. So 4 and then 9, and the next perfect square after 9 would be 16. So what plus 5 equals 16? So we could say 11 plus 5 equals the square root of 16, which would give me 4. So when I plugged in 11, I got 4. Let's go the other direction. What about, let's see here, 1. How could I possibly get a 1? And that would be, what plus 5 is 1? And we could say, well, -4. So -4, when I plug in -4, I get square root of 1, which is 1. What happens if I wanted to get 0? Because I know the square root of 0 is 0. Well, if I plugged in -5, of course. So -5, 5 would give me that. So I've got several points here, so now I'm going to plot them so I can see what my graph looks like. Remember, our domain, we want to keep it positive, so you're not going to see this graph actually go below your axis, your y-axis. So let's plot these. So I have -1, 2. I have 4, 3. 11, 4. Okay, I'm going to throw that one out because my coordinate plane doesn't go that far. -4, 1. And -5. Actually, -5, 0. Not sure why I wrote 5 there. That should have been a 0. So -5, 0. Now you'll see, and if you put this in your graphing calculator, which you could do very easily too, you're going to get a very gentle curve. So it starts, and then it's going to go through all of my points and keep going. So it's just a very gentle curve. So again, you can put this in your graphing calculator since it's in function notation, and you can generate your ordered pairs by using the table feature, or it didn't take us very long to kind of go through and generate our own ordered pairs. So let's look at the one below. It's similar because it still has a square root and it still has a 5 and an x, but the square root's only over the x this time, so that is going to impact our table a little bit. This actually makes this a little bit easier, because now, since it's just the square root of x, I'm just going to think of numbers that I can take the square root of, so all my perfect squares. So when I plug in 0, I'm going to get 5, because the square root of 0 is 0. When I plug in 4, the square root of 4 is 2, and 2 plus 5 is 7. If I plugged in 1, the square root of 1 is 1, 1 plus 5 is 6. Let's see here, I have 0, 1, 4, let's see here, I could plug in 9. If I plug in 9, the square root of that is 3, 3 plus 5 is 8, so 9, 8. So we'll probably get a good idea of what our graph looks like just by plotting these points. So let's see here, 0, 5, 4, 7, and I'm off my coordinate plane, 1, 6, 9, 8, it's going to be kind of out here, and I have a gentle curve. Now you'll notice the curves are the same. One's not really steeper than the other, but what you may have noticed is that plus 5 on this purple graph, that raised our graph 5 units up. Whereas on the first one, with my red graph there, we were actually 5 units to the left. So the plus 5 underneath the radical and a plus 5 on the outside of the radical does impact the graph differently. Now let's look at finding each of these squares. We're not going to do all of these, but the first one, the square root of 100 is 10, and the square root of m squared is simply just m. And I'm going to put absolute value symbols around that to ensure that it stays positive. Now this second one, y squared minus 10y plus 25, is a trinomial that can be factored. And when I factor it, I get y minus 5y minus 5, which I can rewrite as y minus 5 squared. Now because my square and my square root cancel each other out, they're opposite operations, my answer is simply going to be y minus 5. We just have to ensure it's positive, so we put absolute value symbols around it.